Oh, hi, how are you doing?
Oh, good morning.
Good morning.
Okay, we'll get started soon. Okay, any question this time?
Uh, yeah, I actually do have a question.
Yeah, go
So,
ahead. Go
uh,
ahead.
yeah, I've been pretty stuck on our previous assignment, assignment three, and I was
Mm.
wondering if I could schedule like time for office hours with you to go over that.
Right now, you can go over your problem.
I'm mostly
It,
stuck on, I've been trying to get started with it, and I've been like watching the lectures and reading the book, and I'm just really confused on kind of like what I'm supposed to do.
Assignment three.
Yes.
Okay, I remember last time we discussed it, right?
Yes, we did.
Yeah, yeah. And what's still not clear so far? Let me see. Okay,
Um,
don't worry. Okay, don't worry. I'm just questioning myself.
yeah, so
Don't worry. Okay,
okay.
now let me bring it up. Okay, you mean programming assignment three, right?
Yes.
Proposal. Okay, proposal. Okay.
Yeah, I came up with a
Yeah,
project
so
proposal.
what's the problem with this one? This one actually is the similar to previous one. You do have a Scala arm. Okay, you got to get this one done, okay? Because what I would say this week three, week four is another robot. Week four, the programming assignment is modeling another robot. We model a lot of different kind of robots. So week three is a Scala robot. Week four is another one, spherical robot. It's another robot. Okay, so it's just like different robot we model with more technique. You know what I'm saying? So it's actually the same, almost the same, just different robot, different approach. Okay. So anyway, that's actually the importance of this one. You must get it done. Okay. Don't worry. No, because I'm not sure which part you don't know. Can we go over it? Can you talk about what where you got stuck? So first thing is that to get the kinematic diagram done. Are you okay?
Yeah, I'm okay with the diagram.
Yes. Then the second one is to convert the kinematic diagram to the matrix, and then where you are wrong, where you have problem. Let's do this. Okay, let's do this. Let me stop sharing. You share your code. Is that possible?
Yeah, but to be honest, like I don't really have too much, but I can share my screen.
You share your screen for your kinematic diagram. Let's start from there. Okay.
Oh, I have my diagram at home. It's a drawing on paper. I didn't bring
Oh,
it
okay,
with me.
okay. That's okay. That's okay. But how about coding? You don't have access to your computer or something to.
It's not on my computer. I have my computer with me for my code.
Oh, so can you show it now or no?
Yeah, I can share my screen.
Yeah, you share your screen, please.
It says sharing screen is disabled.
Disabled?
Yeah.
Hmm. Okay. I didn't set up that way, so I think sharing screen must be. Let me see. Must be the university may do it. Okay, let me see. Unmute, start, remove participants, chat. Enable waiting room. Let me see. Lock the meeting. Allow share screen. Okay, let me. Okay. You should be able to do it now. That's the default setting for the university. So should be able to share now.
Oh, yeah. Yes, I can. Can you see my screen now?
Oh, it's coming up. It's coming up. Yes. Okay, this Tuesday and Friday session, it is supposed to be a discussion. So we go help student for homework first. Okay. And because the lecture we already pre-recorded, so there's no reason why we should repeat it so many times, right? So well, how is your call? Okay, let's actually go there. Move up a little bit. Move up a little bit.
Oh,
Yeah, move up a little bit. Can you? Okay, let me do it. Okay, wait. Can you share?
oh, sorry. I think I just got disconnected. I'm going to try to share my screen again.
Yeah. Thank you. Sorry for that. Okay. I'm
I can see
requesting
it
for
now.
yeah, I'm trying to request for the control of your PC right now. Can you grant it? Okay.
Yes.
So here you have the import numpy for NP. Okay, you have the EE usually is the decimal point. Okay, A1,
Uh,
A2, A4, you are okay. T1, T2. Okay, if you have the two revolute join, that actually is fine, right? T1, T2 is okay. D is extenders current D. Okay, that's okay. And then you have T1, T2. Wait, your array must have some issue. Your array must have some issue, okay? Okay, so here you have to have, oh, okay, you convert it to, let me see. Right here, you're 34. Is that done so far?
sorry, can you say that part again?
Is that done so far? Is your program just up to this number 3?
Yeah.
Slide 34? That's what you have so far?
Yeah.
Yeah, no problem. Okay, so basically you do have two rotational matrix R 01, okay, R01 and R 12, right? But your actually revolute join is here, okay. I'm sorry, why it actually go away like this, right? Let's assume that the last one you just have the extended, that's actually fine. Okay. So you kind of doing this. Okay, so this one, wait, I'm going away. Did you erase it?
Uh, what is it? I can't really see it.
I'm drawing something.
Oh, I can't see what you're drawing.
Really? Okay. I'm actually wait. Okay. So let me actually try different way. Okay, let me stop your drawing. Okay, let me try different way. Okay, let me try different way. Let me try sharing with whiteboard. Okay, can you see now a whiteboard? So can you see my drawing now?
Yes, I can.
So basically, this one is some robot like this, right? You have extenders. So the last one, you do have this one. You do have a D here, right? The D is the
Uh,
length of here, okay? So you do have a theta 1 here, theta 2 here, right? But something that you need to know is that you do have a frame 0 you need to set up here, right? Frame 0. Frame 1 need to be here, frame 1. Okay. Frame 2 need to be here. Okay. Frame 3 need to be here. Maybe this way. Okay. Maybe this way. Frame 4 need to be here. So they are 3 join and they should be 4 frame. Actually, this is actually 5 frame. 1, 2, 3. Okay, 5 frame. Let's see. Here you do have 1. Okay, we have 3 join. 1, 2, 3. 3 join. And then okay, this one is actually, we don't need this one. We just up to there. We do need to have 4 join, 4 frame. Okay, and this one is a point according to your frame 3, right? Is okay? Frame 2, frame 1. So you need to actually build your kinematic diagram up to here, right? And then assigning proper XYZ to it. Then after that, you need to set up the so-called homogeneous transform matrix. starting from to actually model the whole thing's homogeneous transform matrix. So there should be a homogeneous transformation matrix of between 3 and 2, and then 2 and 1, and then 1 and 0. That would give you the homogeneous transform matrix of H1 to 3. Okay, let's assume that you are actually looking at this one. This one, it should be including 3 part: orientation matrix of 0 and 1, rotational matrix of 0 and 1. Okay, that should be included. You also need to consider the orientation matrix. So at this moment, you only have the rotational matrix, but you do not have the homogeneous transform matrix yet. So you need to solve the problem first here. Okay, so that's actually your problem. Is should be you do not know how to transit from one joint to the other joint. Okay, the portion. Okay, let me take a picture of this one. So far, okay.
Yes.
Okay, let's don't move don't jump so much. Okay, let's just jump do one by one. Okay, let's assume that we are looking only at the first stage and joint one and the base. Let's just look at this one. Okay, so your base frame is over here. Okay, that's this X0, Y0, and G0. Okay, and your this one is your G1. Okay, and then your x must be perpendicular to your G0 and G1, so it must be here. Okay, this is your X0, X1, right? And then your Y1 must be right hand rule, so you need to assign your Y1 to be here, right? Is that okay?
I think so, yeah.
Okay, so here you will have from this one, okay, from this one, let's see. This one actually, when you rotate with theta one, okay, when you rotate with the theta one, right here actually, when you just look at these two, and if there's no rotation for theta one, okay, so the theta one actually 0 for the rotation direction. This one, if there's no rotation for theta one, then your frame would have, you should have a orientation change. So your X0 is here, Y0 is here, your Z0 is here, right? Your actually your new frame X1 is here, Y1 is here, and then G1 is here. Okay, so basically you need to design a orientation matrix based on your X1, Y1, and G1. Okay, then there's an orientation matrix. You get your X0, Y0, Z0, right? So right here, the orientation matrix will be your X0 is your Y1, X0 is your X1. So basically 1, 0, 0, right? Your Y1 is, I'm sorry, your Y0, okay? Your Y0 should be your G minus G1. So minus G1, minus G1. Your Z0 should be your Y1. So the orientation matrix is this one. Is that okay?
Yes.
So even this orientation, so this one you should have if you want to get your X a P frame, if you want to get a certain point, okay, coordinate with respect to if you know about P1, okay, the coordinate with respect to friend one, you want to actually get the coordinate with respect to the frame 0, let's go P0. The relationship of this one would be equal to this orientation metric time that, which is this one. Is that okay?
I think so, yeah.
And this one, because the orientation metric is also one sort of the rotational metric. So you make it as 0, 1, 0, 0, 0, 0, minus 1, 0, 1, 0, and then here 0, 0, 0, 1, 0, 0, 0. To make it a homogeneous transform metric is also okay. And you can also put the SYG 1, 1, 1, 1. It's also okay to add extra colon, and it's also okay, right? Does that make sense?
Can you go over that part again? Like, why would I add in the extra
But
columns?
in extra colon, just because you want to make it as a homogeneous transform metric.
Okay, okay.
This is transform, right? This actually is orientation transform. It's not rotational transform, but when you use it in the homogeneous transform metric, it's the same as your rotational metric. Does that make sense?
Yes.
It's actually no difference. Let me take a picture of this one. Okay, later I can send you the pictures. Okay, that actually go back to the slides somewhere. Okay, I mean actually. So it's welcome to discuss the homework here. Okay, we actually do not offer extra office hour because the primary of purpose of this meeting time is set up for discussion. And then every time, because not a lot of students coming in to discuss, so I just talk about something. And those are something actually is repeating, right? Actually. Let me try to find the slides. Homogeneous transform metric here. So last time there's a time that we actually talk about this one, homogeneous transform metric, right? Originally, your Cartesian plane is this. We set W to be 1, so it's okay. So here, this one, no matter is scaling, rotation, or translation, same. Even orientation is the same. So orientation metric can be put over here as well. You put extra row and column. Should still work. Does that make sense?
Yes.
Okay. So now one we solved. All right. Now one we solved. So let me attach file to here. Okay. Let me see. Let me try to wait here. Can we? Okay. I cannot. I actually in the chat box. I cannot put that. I'm going to send you by email. Okay. Or some other way to send you the file. Okay. Let's actually go back to that. Okay. So this one we finished the orientation part. Right. Let's actually continue to look at the rotation part. Okay. So let me kind of clear it. Okay, one more time. Let's actually try it again. So let's actually draw it a little bit this way here. Okay. Okay. I'm sorry. It actually, this one is actually vertical rebel joint. So previous one, what I'm talking about, maybe it's wrong. Okay. This one actually is this one Z direction actually is this direction. Let me do it. Okay, let me do it. I actually put it in the wrong way. It actually is this way. Let me redo it. Okay, let me redo it. Sorry. So this one's still the same. We still have X0, Y0, Z0. This one is frame 0. Okay. Your frame 1 here, your Z direction is here. Your Z1 is here. Your X, let's assume is here. Okay. Your Y1 should be here. Okay. the good news is the orientation metric should be 1, 0, 0, 0, 1, 0, 0, 1, 0, 1. It's identity metric, so there is no change. It's even easier. Is that okay? So I'm sorry.
Yes, that's okay. Yeah.
I'm sorry, I make a mistake there, technical mistake. So this one we can set up this way. Okay, you write it as this one is still okay. Okay, so this one, let me take a picture. So far, this one is the orientation metric. No problem. This one's simple, and you don't add this orientation metric in there. It should be still fine. So that's actually okay. So now let's look at the rotational part. Okay, let's look at the rotational part. So this one is actually erase it. Erase this portion. Okay, let's erase this portion. We don't need that. Let's look at the rotational part. So now if we do wake up a rotational part, here we rotate by theta. So here, if this rotational rubber joint here, we rotate by theta, what will happen? You rotate by theta means your frame will move by theta, right? Your frame will move by theta along the z-axis, right? Along the z-axis, so it apparently would be what? Apparently, this one would be cosine theta minus sine theta 0, 0, 1, sine theta cosine theta 0, 0. This one is the rotational metric of the theta. But you need to make it as a regular joint. Okay, you need to make it as the homogeneous transform metric. So you add one more label. But right here, no displacement. So right here, your x1, y1, z1, 1, s0, y0, z0, 1. Okay, this one is P1. P1 is here with respect to the frame 1 and after rotation theta. You should get the coordinate of this one with respect to the frame. This one's P0. Is that okay?
Yes, I think so.
That's the one you need to use. Then that's it. Then you actually finish your H01. Then you do it one by one and multiply them together. That's it. Right?
Right. Yeah.
Yeah. So this one is the first one. Second one, still be easy. The reason why I pick this Scala is that Scala has an advantage of Z doesn't change direction actually. The good news is that we do not have orientation metric until the last one. So let's look at the second stage. Okay. Second stage, you do not need to worry about the frame. So frame 0, you don't need to worry about it now anymore. You actually just forget it. When you talk about stage 1 and 2, then your frame 0, you do not need to worry about. Frame 0, you actually already represented by the H01. Okay, so that one you do not need to worry about. So this one is okay here. Now you actually set up a new frame. This new frame, Z direction still this direction. X direction still this direction. Y direction still this direction. So no orientation. So far, no orientation, right? So you still turn another one by theta 2. So the metric is the same, except that theta1 replaces the theta2. Is that okay?
Yes.
Theta2 replaces the theta1, I'm sorry. So that's the second stage. So this one, okay, you should be able to get your H12 now. Okay, so that one we actually do not want to waste our time. Let's actually take a picture. That's it. Now let's move on to the next stage. So next stage, you do have the orientation problem now. So let me actually erase this one. We no longer worry about H12. Now we worry about H23. Okay, H23. So this H23, let's assume that you actually do have this one. You have extended here is this direction going down here. So your Z direction now is actually this direction is your Z. Okay. Z3 is this direction, right? And your X need to be perpendicular to the previous one. So your X, if you want to use this one, that's actually okay. So let's assume that is X3. So X3, Z3, you need to use a right-hand rule. Right-hand rule. So right-hand rule, your Y2 must be in this direction. So you can cross product here, and then you're pointing down, right? Your palm here, okay. Your finger this way, your palm facing this way, your thumb would point down, right? Is okay? That's a right-hand rule, cross product direction. Okay, so is that okay so far? Right-hand rule.
Yes, I think so.
So that one actually is okay. So you get this one down. Okay, right-hand rule down. So now you have a D, but you do not have rotation now, and you actually need to worry about the orientation first. So the orientation metric is not hard. Let's look at it. Your S1 should be your S3. S2, I'm sorry. S2 should be your S3. Okay. Your Y2 is your minus Y3. Your Z2 is your minus Z3. So your transformation metric, orientation metric is S3, Y3, Z3, 1. And here you do have S2 is equals to S3, so it is 1, 0, 0. Y2 equals minus Y3, so it is this one should be minus 1, 0, 0. And last one is minus 1 here, 0, 0. Okay, and that will give you your X2, Y2, Z2, 1. Let me rewrite it, okay. Let me rewrite it. You should add another extra direction here, okay. Okay, so far is the transformative, but remember that you do have an extended D over here. Extended D is on your Z3 direction. Extended D is on your Z3 direction, right? So your D is this direction, this D. So this one actually, this one here is your D should be put here. That's it. So your new matrix should be 1, 0, 0, 0, 0 minus 1, 0, 0, and then 0, 0 minus 1, D, and then 0, 0, 0, 1. This one is your homogeneous transform metric for the H23. The only difference is this portion is orientation metric. This portion is your displacement vector. That's it.
Okay. I think that makes more sense to me now.
Okay, so you just sum it stage by stage. Every time you should be able to sum. So you see that actually, if you want to control your robot, okay, it's not robot game. Okay, robot game you just use your joystick, right, left, right, and you control it. And you do not need to be that accurate. But when you do programming or controlling your robot by a program, you got to use this kind of metric to control it, right? It's a totally different level of the things. Is that okay?
Yes.
Okay. So try it, okay? Think about it. Number one, Usually, if your number is wrong, I don't deduct too much. Okay, I look at how you solve it. I mean, numerical error, everybody may make those kind of mistakes. Even me, sometimes, you know, there's so many numbers, you miscalculated, it's okay. But do not try to just do number fitting, okay? Some students do number fitting, don't care about how you come up with it. But do number fitting, that's the wrong way to do things. Is that okay? So basically, what you need to do is to set up your rotational metric, orientation metric, on each stage, put it over here. Displacement vector, put it over here. That's it. That's all you need to do. Is that okay?
Yes, it is.
And put the extra line here. Then you need to extend your what? You need to extend your metric. Yes, you need to know how to make your metric bigger. One more row, one more column. Yes, is that okay?
Yes.
But that's not that hard. So that's why in the very beginning we teach you what is the metric operation before we go into the discussion. Okay. So any more questions so far?
I don't think so.
Okay, so that is about homework. Okay, so the only thing that I can say is that you must do it. Okay, do it and then you will learn. And still have questions, you still can ask me. Okay, no problem.
Okay.
That's actually the homework discussion. So this week we are in week 4 already. So here, okay, whatever I say right now for the lecture will be repeated. Okay, or we already have the pre-recorded video, so you can also look at that. I don't spend the whole time just trying to teach it again. So you should try to work on homework, and we welcome all kind of discussion for the homework. Okay, you're welcome. Okay, and here we actually have this one called differential kinematic. Differential kinematic, because so far we are talking about, okay, that's actually we talking about the displacement, primarily the location of XYZ. The location of XYZ, as we know, the location of XYZ actually is the displacement, right? And then if you do the first derivative, you got your velocity, speed or velocity. If you do second derivative, you get the acceleration. Okay. Okay, what's the difference between speed and actually velocity? And Nick, do you still remember in physics?
I do not remember.
You do not remember? The difference is speed is vector, velocity is a scalar. So what is the difference for these two? What's the difference between scalar and the vector? Are you okay? So let's assume that we are in the two-dimensional space. We do have a vector, and this vector is called x naught, y naught. Okay, so this one is a vector. So let's call this vector as g vector. Okay, so g vector is like this. Okay, and when we talk about velocity, velocity actually is equal to square root of x squared, s0 squared plus y 0 squared. Okay, we talk about the scalar portion is that is, so it's actually is the r, is the length. It's the length. It actually is the absolute value of this vector. Okay, and then vector you should have also have a direction. So if this one is theta, it would be equal to r times cosine theta minus h sine theta. Okay, So speed, you do have direction. Speed, you do have direction. Velocity, you don't. Okay, velocity is just the absolute value, the total amount quantity. So this portion we call it scalar. The whole thing we call it a vector. Is that okay so far?
Yes.
Okay, so that's the definition when you do physics. Any vector and scalars main difference is like that. Okay. Okay, so that's that. So that okay. Now let's go into the differential kinematics. So right here we will like to look at the derivative. Okay, you would like to do it derivative, and Jacobian metric is to actually calculate the derivative in a systematic way. That's what you should understand. The goal, okay, we have the forward kinematic that is from your joint variable to find its destination XYZ. Okay, that's a forward kinematic. Inverse kinematic is from the desired or expected XYZ, calculate back to the joint variable what it should be. Okay, and that's actually is inverse kinematic. Now we talk about differential kinematic. Differential kinematic is like, let's look at the speed or acceleration. That is the taking the derivative, taking the differential thing. Okay, so derivative of a rotational metric is expressed in terms of n effector angular velocity. Okay, so what? So there's an angular velocity, there is a linear velocity. Linear velocity is talking about how fast you move, okay? Angular velocity just talking about how much theta you rotate. There's a scene, you do not move, but you still want to see how much it rotates. That's called angular velocity. Is that okay?
Yes.
So, and why this is important is because that we do have that airplane scenario. We do have an airplane. Okay. And this guy do have a certain, according to a certain frame, it should have certain XYZ. And we say this XYZ is location, right? But along its x-axis, y-axis, and z-axis, okay, y-axis should be this way, I'm sorry. It is right-hand rule, okay. Okay, so you with these three direction, you should have the roll, pitch, and yaw, right? So you would do rotation. So you also have the theta x, theta y, theta x, theta y, theta z. Is that okay? So airplane will have 6 degrees of freedom. So in a way, this airplane's real condition, it may be flying in this way, right? If you look at the Second World War, Japanese airplane to bomb the Pearl Harbor, they always try very low, very strange angle. Oh, that right. So that actually have angle still be a very important control factor, right? So that actually airplane has a 6 degree of freedom. Okay, whatever. So that is the what we want to control, and that's what we want to control. Okay, anyway, go back. Okay, so that actually you need to spread your rotational metric in with the angular speed. Okay, velocity composite rule is actually characterized and then contribute the joint velocity to the linear and the angular velocity are computed. Okay, so that actually is the goal is to calculate for the linear and the angular velocity, and formula for prismatic and revolute joint are derived. So we want to use a Jacobian metric to sum to get these two joint. This a little bit complicated. Okay, this portion Jacobian computed. So Jacobian is a algorithm, just like the Denby-Hartenberg matrix. It's just want to come up with an algorithm so you can systematically solve the problem. That's the goal, the whole goal. Okay, so kinematic diagram, differential kinematic relationship between the joint velocity and the end effectors linear and the angular velocity. Okay. Jacobian is derivative of a rotational metric, Jacobian computation. Okay, these are something we want to study. Okay, let's see. Let me try to go to something that actually, okay. This portion we have a lot of math. That's actually, okay, let me see. Let me try to go to somewhere. Okay, let me try to bring up the other note. Okay. The introductory note, not using this graduate school note. That is sometimes too hard. Let me look at the differential kinematic. Okay, so here this one is differential kinematics. Let me find an appropriate page. So here we are looking at the differential kinematic. And we want to look at the friend-to-friend transformation and the angular velocity and displacement velocity. Okay. So the thing is that you do want to take derivative. So you do have dt. Okay, let's say q. Let's say is a p. Okay, so let's assume that you have the two tensor. Okay, that's t1 and t prime. Okay, so your d tensor will be equals this h minus this whole thing. There's a calculation here, and eventually there will be a matrix times your tensor. That's the goal. Okay, that's the goal we want to have. So T is a friend, is a set of axis to the base axis, and small differential displacement of these axes, dp, dq, okay, relative to the base axis will cause the difference. Okay, so yet T primes equals T plus dt. dt by itself is a vector. Okay, it's a tensor. And that you can actually formulate it by the metric time. Okay, that's the goal. Okay, that's the goal. And that is the goal. So we try to come up with differential transformation metric. So originally we do have the so-called homogeneous transform metric. And then we take derivative. Okay, we take derivative, we will get such a metric. Okay, we'll say get such a metric. So there's a velocity metric. So if you look at only the velocity metric, the omega is like this. Okay, that's your angular speed metric. And then you also have the displacement on the p row. Okay, and that is the the transform metric you come up with. So basically, that's a differential transform metric is like this. You do set up this different term, you get it. Okay, here. Okay, so this one, if you look at the displacement and the rotation, is something like this. Okay, anyway, this one I try not to impose this different transformation metric to it. It's a little bit too hard, but you just understand that actually is trying to calculate the derivative. Okay, so here, right here, we actually so let's assume that we do have a a point P. Okay, it's a 350 with respect to the frame C. So frame C is the last one. It actually we should replace to this one. Okay, and this point actually rotate in the 2 rod per second. 2 radian per second is what? Angle is measured by the radian. Okay, so it actually is rotating. The frame is rotating in a speed of 2 radian per second speed. And let's look at, okay, in that case, this point is what? It is 305 with respect to frame 1. And this frame 1 is rotating at 2 radian per second speed. Using this one, and we are trying to calculate it. So in conventional way, you need to set up the metric to solve it. So this one is pretty hard to do. So we can come up with the so-called differential solution, calculate the omega metric, and then you should be able to get the answer faster. So the key point is that you got to find your differential metric here. And this one would be able to calculate your velocity of the with respect to your frame 0 with the rotational metric and displacement, okay, and also the so-called this one I think is actually displacement radian. Okay, this one's 2 radian per second. 2 radian per second. This 2 is its relationship with the frame location. Okay, 2, 3, and 0. Okay, T is this one, 2, 3, and 0. So this is no change, and there's the data. So this portion is your friend. Your friend have no rotation. So this friend rotation is identity metric. Friend displacement is like this. Okay, and this delta. This delta is your displacement. Your rotation of the caused by the rotation of what? Rotational of your frame. This 2 radian per second one. Okay, so here this one is 2 radian per second. You will cause the delta metric to be like this. Okay, and then your frame to frame difference will be your T. Okay, and these 2 equations, where it came from, is the one we do derivation here. It actually is, this one is the equation we derive for the rotational speed and also the displacement velocity. Is that okay so far?
I think so, yeah.
Yeah, okay. And the background math is really hard, okay? Background math is really hard. So just understand that whatever at the very end we use to calculate the metric is that this delta is the transformation caused by this the 2 radian per second. Okay, and the T is caused by the displacement. I'm sorry, not displacement. The frame C to the original one, and your W is a vector. So W is what? W actually is 350 vector, and then with that you time together, you will get this velocity. Okay, is that okay? 350 is your point direction. So the whole theory behind this differential equation, differential kinematic is, first you need to know about the tiny displacement change. Okay, it's kind of dq. This one is actually taken by this. Okay, H actually is a system function. It's a system function. So one thing you need to know is that your delta t, okay, your locational change will be equal to your original location plus dt, right? So your dt should be equal to your t minus delta t, right? So that is, and if this delta can be replaced by a metric, so this whole thing will become the difference metric times the initial one is t. So this d will be this differential term. It actually, this one is identity. This one actually is what your t here come from. Okay, is that okay? I'm sorry, I write in the opposite way. Okay, this one should be your. This one after you move it, it should be your dt should be equals to your delta t minus t. Okay, so this portion is your delta t. This portion is your t. T is the identity metric times t. So it actually become a d minus t, and this d actually is h dp dq dp. Okay, minus I. I is identity metric. Here, this one is a systematical function. Okay, putting your displacement on Q and P. Q and P are two. It actually representing your state variable that actually your theta and your theta and xyz. What is called theta is rotational. P is the displacement. Okay, so it's the theta. Basically, it's a metric of the displacement and the rotation. Okay, so anyway, that's the basic idea of what this one is. Okay, and those things you can, based on this deviation, you try to calculate it. Okay, d sin theta dq and actually cosine dq. Okay, whatever, you will get this rotational change as such. Okay, so as you can see, this one is your d theta, your theta change. Okay, your theta change, and its cost. It actually costs how much change in your XYZ. Okay, the last one is your XYZ positional change. So that is the metric we are looking for. That's a delta metric we are looking for. Okay, that's a delta metric we are looking for. And this one, if you formulate it into the omega format, that's only the rotational part is this one. Okay, and this metric is including the rotational part and the displacement part, and then put them into the homogeneous transform metric. Okay, and that's the continuing to derive it. Okay, so anyway, after the long derivation and also cross product, a lot of things, eventually it comes to such a equation. Velocity equals your rotational your rotational change times the metric of displacement reference frame times your times this one is your what? Your frame one's coordinate. This one is your frame zero's coordinate, and there is a rotation on the frame. But the rotation delta is here. The frame to frame difference is here. Is that okay so far?
Oh yeah, I
Hello.
think so.
And this scene actually eventually will be the one we see here when we apply to the equation. If you don't want to do that, you want to use your trigonometry and complex number to solve it. Yes, you can do that, but it takes a long time to finish. Is that okay? Okay, so this portion is kinematic, differential kinematics. Okay, let's see. This one is the differential kinematics. Okay, that's actually same. Okay, and there's an inverse differential kinematic. That would be the Jacobian. Okay, that would be the Jacobian metric. Okay. So this one, I'm going to talk about it on Friday. Is okay? Okay, this is too much. Okay, too much right now. Can we discuss it on Friday? For the Jacobian. It actually is a whole algorithm. It take a long, long time. Okay. Okay, can we finish today here? Any more questions?
I don't think I have any more questions. Thank
Okay,
you.
so work on the homework. If you still have question, you can still see me on Friday. Okay. And then Friday we'll discuss the Jacobian. Jacobian take a long, long time to discuss what it is. Okay. It's actually harder. Okay. Okay, that's it for today. Thank you. Bye now.
Thank you.
Bye-bye.